Hello, everyone. Welcome to week 10 of this course. In this week's experiment, we're going to look at passive filters made out of resistors, inductors, and capacitors. So first of all, let's ask the question, what is a filter? And the answer is simple. It's a device or a circuit that selectively lets signals through. The idea is quite similar to the idea of a water filter that you might have at home. In a water filter, you give it some input, which is the water, and then it lets through just the water and blocks any contaminants, right? So the output is pure water minus the contaminants. So the same idea applies for electronic circuits as well, but here the filtering occurs in terms of frequency. So if we apply a signal that has a broad range of frequencies in it, then due to the action of the electronics filter, the output of that circuit will only contain some ranges of frequency, and it will block certain ranges of frequencies of the input. Now, then what is a passive? What do we mean by a passive filter? Right? So a filter that does not use any active components and only uses passive components, such as resistors, inductors, and capacitors, is called a passive filter. Active component means any component that requires external power, for example, op-amp or MOSFETs and BJTs. Resistors and inductors and capacitors do not require an external power. So an example would be, say you have a simple filter like a Brita filter, that's a passive component. You don't need to hook it up to any power. You just add water to it and it will filter the water. But if you have a more sophisticated water filter that, for example, uses UV light to kill bacteria, then that filter needs to be hooked up to power, and it needs some external power to perform its filtering action. So that is what we might call an active filter. And the analogy carries over to electronic circuits. Okay, so how do we then create such frequency selectivity in circuits? And the answer is we saw that inductors and capacitors have this differential relation between voltage and current, and we can leverage that differential relation between voltage and current to get frequency specific behavior of capacitors and inductors. And to see just that, we will do this quick exercise. But before we go into it, you need to recall a few things. So first is the Fourier decomposition. Fourier decomposition is basically a theorem that says that any periodic signal can be broken down into sines and cosines of its fundamental frequency plus its harmonics with different amplitudes, right? So any arbitrary periodic signal can be broken down into sines and cosines. For example, a periodic square wave can be broken down into its component sines and cosines. A triangle wave can be broken down into sines and cosines. Any arbitrary periodic signal can be broken down into sines and cosines. We can take it further and take the limit of the period to be infinite, and that way you can, in fact, also decompose any arbitrary non-periodic function into a spectrum of frequencies, spectrum signals with all frequencies, all different frequencies. Right, so that's Fourier decomposition, basically saying we can decompose any signal into different frequencies. And then we have superposition, which is saying that you can analyze a circuit by analyzing one individual voltage source at a time and then putting together all the voltages to get the overall output of the circuit, right? So using these two, both of these two together, the Fourier decomposition and superposition, what we can do is we can study the action of a circuit on any arbitrary, due to any arbitrary input. The steps would be to first break the input into its component Fourier components and decompose it into its Fourier components, different frequencies, and then study the frequency behavior of the circuit. How does the circuit behave at different frequencies? And perform the analysis for each component, Fourier component of the input signal, and then reconstruct the output using superposition, right? So simply add the outputs, all of the outputs. And that way we can get the output of the circuit due to any arbitrary input to the circuit. Okay, I said that using Fourier decomposition, you can break it down into sines and cosines, but in fact, it's better to actually decompose this cosine into these two oscillating exponentials. And this we can get from Euler's theorem. Here, omega is simply 2 pi times the natural frequency, and j is the imaginary unit of -1, square root -1, right? So we can study the circuit for in an arbitrary frequency omega, right? And input e to the power j omega t with any omega that you can think of. Okay, so let's look at what happens when the voltage across the capacitor is e to the power j omega t. We know that the current through the capacitor is C times derivative. And if you do that exercise, what you'll see is that the current through the capacitor is J times omega C times the voltage across the capacitor. And now if you take the ratio of the capacitor voltage and current, you'll find that it's 1 over J omega C. Okay, so previously what we said was that the ratio of the voltage to capacitor, voltage to current is this quantity called resistance. But now for a capacitor, you see that this is first of all, you should notice that it's a complex number. And so when we have a complex resistance, we give it a different name and we call it impedance. And the second thing you should notice is that this impedance is frequency dependent. And so this very fact that the capacitor impedance is frequency dependent and frequency aware is the fact that allows us to make frequency selective filters. Okay, so let's look at this RC circuit that we've seen before. So if we want to analyze the circuit in the frequency domain, we just need to convert all of the components within it into its what we call the phasor counterparts. So capacitor, we can replace it with an impedance of 1 over j omega c, right? And then in order to calculate the output voltage, that's the voltage across the capacitor, we simply need to do a voltage divider. If you do this voltage divider, you'll find that V out, the ratio of V out to V in is 1 over 1 plus j omega RC. So notice this product of RC that we've seen before. This is our friendly time constant tau. Right? So we said that an RC of the circuit gives us a characteristic time scale of the circuit. But as we know, frequency is simply 1 over time. So this RC product also characterizes the range of frequencies that the circuit was going to filter in or out. Okay, so again, if we rewrite this as V out is equal to something times V in, we see that this division factor now is a function of frequency. So different frequencies, you get different amounts of output, even though you have the same amount of same amplitude of that frequency. Okay, but now this gain, it's a complex number, right? So how do we interpret the complex gain? Now, any complex number, a plus ib, can be expressed as some magnitude and some phase angle, okay? So this is a Cartesian representation, and this is a polar representation of the same complex number. But the way to read it as is this magnitude of the complex number. It causes amplitude multiplication or amplification. And this phase factor, it causes phase shifts in the signals, okay? So if you had a gain of 3 with a phase of pi over 2, then the input signal will get amplified by 3 and its phase angle would be shifted by pi over 2. So that means a sine will become a cosine, or a cosine will become a negative sine, and so on and so forth. Okay. So for example, here V out is this multiplication factor times V in. We usually write this this multiplication factor as h of omega, or and it's sometimes also called the transfer function. Now you can write this, this is right now in the form a plus ib. It's in Cartesian form, so it has a real part and an imaginary part, but you can break this down into its polar form, where you write the magnitude written as h omega magnitude and e to the power 5, the phase, and the phase is simply negative tan inverse of RC. Okay, so this is all coming from the knowledge of complex numbers and conversion between Cartesian and polar coordinate systems. Okay, so this is what we call the magnitude of the gain, and this is what we call the phase of the gain. Okay, so now let's see how this acts as a filter. Okay, so this is the multiplication factor, or the gain of the system. And I'm working with the same example of RC circuit that I looked at before. If you change that circuit by a little bit, move things around, then this multiplication factor, this h of omega will be different, obviously, right? So so how does this act as a filter? Now for low frequencies, if you think omega is closer to 0, so what happens to h of omega when omega goes closer to 0? You basically lose the imaginary component and you're left with 1 over 1, so the gain is 1. But for high frequencies, what you will see is that this omega, if it goes to larger and larger values, then this imaginary component becomes larger and larger, and this 1 is negligible. So what you're left with is 1 over j omega RC. If you take the magnitude, you're left with 1 over 1 plus omega RC. As you keep increasing omega, this factor becomes smaller and smaller and approaches 0. Okay, so basically what we see is that for higher frequencies, this factor approaches 0, so the output approaches 0. Whereas for low frequencies, this factor approaches 1, and so V out approaches V in, right? And that way, we used it as a filter that only lets low frequencies through and blocks high frequencies, also called a low-pass filter. Okay, so if we wanted to look at the same thing but in a pictorial form, we look at the magnitude of the h omega as a function of omega. We can do this plot because we have the analytical expression. And so this graph should actually continue on the left-hand side because this is a logarithmic scale on the x-axis. Okay, but basically we see that for low frequencies, you have a gain of 1. And as you keep increasing the frequency, the gain drops to 0. Now, one natural question to ask is, we said that something special should happen at omega equals RC because it's a characteristic time scale. So let's look at what happens there. So at omega equals to RC, if you replace that in the expression that we have, then you'll see that the output to input ratio becomes 1 over square root of 2. That doesn't seem like anything special, but if you think about power, power is voltage and goes as voltage squared. So at this point, the power ratio of the two signals would be 1 over 2. Okay? So at omega equals RC, the power measure of the two voltage input and output, the ratio will be 1 over 2 or half. Okay, and this frequency where, I should have said omega equals 1 over RC here, where omega equals 1 over RC, that's given a special name. It's called the cutoff frequency, or more specifically, the -3 dB cutoff frequency. And the reason is it basically indicates where the power drops by half. Beyond that, the power or the voltage keeps decreasing, and above that, the power is above half the input power. Okay, so this is a good indicator of where the frequency selectivity begins. Okay, so you can rewrite this expression now in terms of the cutoff frequency, and you give away all of the circuit parameters for just the system parameter of omega c, and and so this is another form you can write it in. Okay, so now if you read the book, you'll come across this scale, decibel, to express gains. So if you look at this picture over here, you have the gain expressed in volts per volts, and you see that there's things happening here. But as you go towards the higher frequency, anything that's happening here is sort of you can't see really properly because it's all going to zero. So instead of writing gain in volts or volts, if we have a logarithmic way of writing the gain, then you can actually see the minute differences in things that are happening at closer to zero gain, right? And sometimes that's important to understand when you're making different applications, doing different applications. So decibel is a scale that a unit that allows us to do that. A bel is basically a logarithmic ratio of two powers. But bel is a very large unit, so instead we will mostly end up using decibel. Basically 10 decibels equals 1 bel. So if you need to convert a ratio of two powers to decibels, you would simply take the logarithm and multiply it by 10. And that will give you that ratio in units of bel. Right? So for example, if you had power 2 as 10 times power 1, then the ratio is 10. And so you have log 10 times 10, which is equal to 10 dB. Okay, so a power ratio of 10 is equal to 10 dB. And instead, if you have a power ratio of 100, then you'll end up with 20 dB. So every factor of 10 is equal to 10 dB. Okay, of power. Right? So now how do we express voltage gain in terms of dB? Because we said that bel is a ratio of powers, but we have a ratio of voltages to work with. Okay? So the way to do that is to convert the voltage gain into a power measure by assuming that, by considering the power dissipated through the same resistor for the given two voltages. Okay. So what I mean by that is if you have a voltage gain, GV, V out over Vin, then you first consider the power gain, power ratio due to the two voltages across the same resistor. Right? So that will give you V out squared over R divided by Vin squared over R, and you end up with V out over Vin whole squared. Now, this is a ratio of powers, and you can convert that to dB by taking the logarithm and multiplying it by 10. And if you take this 2 out of the logarithm, what you will get is 20 times the log of V out over V in, which is the voltage gain. So this is an expression you can use to convert gain in volts per volts to gain in decibels. Right? And now, some common conversions are listed here. So basically 0 dB corresponds to a gain of 1. So think about that. 0 dB is not a gain of 0. Be careful there. A gain of 10 volts per volt corresponds to 20 dB. Another factor of 10 will give you another 20 dB. So 100 volts per volt is equivalent to 40 dB. If you do division instead, you simply change the sign. So 1 over 10 volts per volt is negative 20 dB. 5 volts per volt is 14, so on and so forth. Now this is where the important stuff comes in. Square root of 2 volts per volt is about 3 dB. And so 1 over square root of 2 comes out to negative 3 dB. Right? So we just saw that at omega equals 1 over RC, the voltage gain was 1 over square root of 2, which corresponds to negative 3 dB. Okay, so negative 3 dB corresponds to half power. Okay, and lastly, if you have a gain of 0 volts per volts, or that the output gets completely nullified, then in terms of dB, that would be a gain of negative infinity. Okay, so if you redrew the circuit again, earlier circuit, then you'd see that the gain is 0 volts per volts, and then you start going into negative infinity dB. Right? So it's no longer saturating to 0 volts per volts, but instead it's going to negative infinity decibels. Now, quickly think about what this value should be if this is the DC or the low frequency gain in terms of decibels. Right? So the gain was 0 volts per volts. So in terms of dB, this should be, this was not 0 volts per volts. So this was 1 volts per volt. So in terms of dB, this should be 0 dB. And similarly at the cutoff frequency, we had a gain of 1 over square root of 2, and that corresponds to 3 dB, negative 3 dB. Okay. Okay. So when doing this lab, you'll come across this term called frequency response. So this frequency response is basically what we just drew. Okay, so this is the magnitude response because it's plotting the magnitude of the gain or the transfer function as a function of frequency. And if you plot instead the phase of this complex gain as a function of frequency, then that's called the phase response. That's called the plotting the phase response. And if someone tells you to plot the frequency response, then you just make both of these plots. Okay, a magnitude response and phase response. It's nothing, it's just the plot of the transfer function itself. Okay, so different types of filters based on frequency passband. So we just looked at a low pass filter, which allowed low frequencies to pass through and it blocked higher frequencies. You can have the opposite of that, which is called the high pass filter, and it will block low frequencies and only pass high frequencies. You can have two different combinations of that. A bandpass filter which blocks low frequencies and high frequencies, but allows a middle range of frequencies to pass through. And those types of filters are called bandpass. And you can have the opposite of that, which allows low frequencies to pass through, high frequencies to pass through, and blocks a range of frequencies in the middle, right? And that's called a band reject filter. Okay. So now the question is, how do you measure the frequency response of a circuit? Basically, what you need to do in order to measure the frequency response is you need to measure the response of the circuit at different frequencies. You can do that by using option 1, which is using the oscilloscope. And that basically means you have to measure the output voltage and the input voltage and then take the ratio to get the magnitude of the gain. And in order to get the phase difference between the two inputs, two signals, you need to measure the time delay between the zero crossings and the ratio of the time delay by the period times 2 pi will give you the total phase difference. Okay, in lab equipment, not your 82, in the lab equipment that we have at the university, the oscilloscopes can make this measurement by itself, but 82 does not have that feature, and you have to resort to measuring that time delay between zero crossings and calculate the phase that way. Okay, so once you've calculated the magnitude and phase difference for one frequency, you change the frequency and repeat this. Okay, and then in order to get the whole curve, you need to measure this gain and phase at different frequencies. And that becomes a very tedious process. So instead, what we will do is we will use option 2. I will recommend that you use option 2, which is using another instrument within the 82 called the network analyzer. And this basically will automate the above process, right? So it will take a frequency, measure the input and output, take the ratio, change the frequency, and so on, and continue that for whatever range of frequency that you say you want the response for. And it will actually also make a plot, both the magnitude response and the phase response. So it's a very, very useful tool. So later on, I'll give you a quick, I may give you a quick demo of this. So stick around. Okay, I guess that concludes everything I had to say. Let's talk about the lab task specifics. Okay, so starting with the pre-lab, the first question you're asked to plot the magnitude response of the different filters in tasks 1 through 3. And basically what that means is you will have to derive the analytical expression for each filter and then plot it using MATLAB. So you only need to plot the magnitude response. And the second question, you're asked to identify whether the two filters are, what kind of filters are the two filters? So are they low pass, high pass, band pass, or band reject for the two filters in task 4. So let me show you what task 4 looks like. So this is task 4, and it's a huge circuit, but the filters only come towards the end, okay? So these are the two filters. The first filter composed of capacitor, and then an inductor and resistor in parallel. The second filter is composed of an inductor and a capacitor and resistor in parallel, okay? So you will do the more analytical version of trying to find the transfer function for each of these filters later in the lab. But for the pre-lab question, you can just answer the question qualitatively based on your understanding of the impedances of capacitors and inductors as a function of frequency, right? So you don't need to derive the full analytical expression for the gains of these filters. And just answer this question qualitatively. Okay, so task 1, as the title suggests, you're building an RC low pass filter. Now, RC filter, you're designing component values given the cutoff frequency. You know the relation between cutoff frequency and the RC values. But just keep in mind that this is given in kilohertz or natural frequency, whereas 1 over RC is 2 pi times the natural frequency. So So don't forget that factor of 2 pi. Okay, so steps 4 and 5 is asking you to gather the data so that you can plot the frequency gain and phase frequency response. And you can use the network analyzer for this part, right? If you want to keep a record of the magnitude and phases, then you can export the data from the network analyzer, and I'll show that to you in a bit. Step 6, you're asked to measure the 3 dB point on an oscilloscope. So this step must be done in an oscilloscope. Basically, you're adjusting the frequency and observing the output amplitude and making a note of when that output amplitude reaches 1 over square root of 2 times the input amplitude. 1 over square root of 2 is approximately 70%. So you can use that as an indicator. Okay, but step 6 must be an oscilloscope picture. Task 2, where you're doing the same exercise, but with the capacitor and resistors position swapped, and that basically gives you a high-pass filter instead. Right? And you're doing the same exercises. Steps 4 and 5, you may use the network analyzer. Steps 6 and 7 must be in the oscilloscope. Task 3 is a band reject filter made out of inductor, capacitor, and resistor. And you've been given the component values for this circuit. And for using these component values, you've already calculated the analytical expression for the gain. And if you've done the pre-lab, then you know what the gain frequency response of this looks like. But it's a band reject filter, so you know that it should have some rejection band. But the center of this rejection band is what we call the resonant frequency, basically because at that frequency, the circuit completely absorbs that frequency. Okay, and that resonant frequency will come out to 1 over square root of LC. Okay. Okay, so here, I'd just like to point out that it says to measure the frequency response for a range of 10 hertz to 100 kilohertz. Change that to 1 megahertz because you won't be able to see all of the features of the magnitude response by going only up to 100 kilohertz. Okay, so this whole thing you can do using the network analyzer, and I would highly recommend using the network analyzer and not the oscilloscope because it's going to be a lot of points that you need to take. Okay, and specifically to find the resonance frequency, you may need to zoom in on the frequency scale and take finer steps because the function is very dynamic at that point, and there's a lot of changes happening. So you need to get much finer resolution of frequency to see the resonance frequency properly. Okay, so measure the 3 dB bandwidth. Again, so this is a band reject. So it's going to have 2 3 dB frequencies, and you can measure these both. And the band of frequency, the difference of the 2 3 dB frequency is what we call the bandwidth. So 3 dB bandwidth. Now the quality factor is simply a ratio of the resonance frequency to the bandwidth of the resonator. This basically tells us how sharp that peak is. And so the quality factor of the resonance. Okay. So task 4, we have 2 filters following this preamplifier circuit, but the filters are only at the end. So your analytical stuff will only consider this circuit, capacitor, inductor, resistor circuit. And typically this is meant to be to drive an audio speaker, but since you're not in the lab, instead you'll just replace the speakers with a 10 ohm resistor. the input signal will still be applied at Vin over here. But when you're measuring the filter response, you need to measure the ratio of the output of the filter measured at the resistors to the input of the filter, which will be measured at this node labeled Vamp. Okay, that's because the input of the filter is in fact at this node and not all the way out front. Okay. So for this, you'll be using an audio amplifier called LM386. Now, be careful. This has a very different pinout compared to the pinout for the other amplifiers that you've used before. So be careful and look up the pinout for this particular audio amplifier. Okay. So here, one thing I'll point out that step 3 is a purely analytical exercise. There's no measurements here. You will be measuring the 3 dB points in a later step, but here you're just doing the analytical exercise of coming up with the transfer function for the filters and setting that equal to 1 over square root of 2 to find the 3 dB frequencies. Okay, so similar to what I showed you for the simple RC circuit, but now you're doing it for this 3-component filter instead. Okay, so this is step 3 is a completely algebraic exercise. Step 4, you're going to construct the circuit and then measure step 4 is just constructing the circuit. But again, instead of the tweeter speaker RSP, see the footnotes, it tells you to replace that with a 10 ohm resistor. Okay, so measure the 3 dB points. Now you use the network analyzer to measure the frequency response and then calculate or measure the 3 dB crossover frequencies for each of these filters. Okay, and now one point to note here is this footnote C. So you only have a single 1 millihenry inductor in your kit. But if you were to make the circuit, you need 2 1 millihenry inductors. So what you will do is instead, with your single 1 millihenry inductor that you have, you will make one filter, do your measurements for that filter, and then you will make the second filter and then do your measurements on that filter, right? Because these filters are in parallel, you can actually add them one at a time and it doesn't affect the performance of the other filter. Okay. All right, so that is lab 10. If you have any questions, do let me know. Next, I will just give you a quick overview of the network analyzer tool on 82, so stick around. So now I'm going to quickly show you where to find the network analyzer and what it looks like. So so far you've used the oscilloscope and wavegen, so far and so forth. So you will still use the wavegen to set up your input signals. But when it comes time to measuring and then plotting the frequency response, then what you will do is instead of going to oscilloscope, you will go down here that says network analyzer. And so here, the network analyzer measures both with channel 1, it should measure the input, and channel 2 should be measuring the output of the circuit. And then it will use channel 1 as the reference. So channel 1 should always be at 0 decibels, and channel 2 will be plotted as a with reference to channel 1. So if it is 10 times smaller than channel 1, then you will see it at minus 20 dB, and so on and so forth, right? So, but this tool right here is showing you the gain response on top and the phase response on the bottom. And you can give it the different frequency range. So for example, if you wanted if you wanted to go from 10 hertz to 1 megahertz, and how many points per decade. So your task specifies at least 5 points per decade. So I'll give it like 20 points per decade. And then if you run it, then this is going to be slow for the low frequencies, but we'll pick up. All right, so now it's changing the frequency, measuring different things, plotting, changing the frequency, measuring stuff, plotting, and so on and so forth. And so you see here, this is the frequency response that we get. Now, in order to, if you wanted to measure the 3 dB frequency again, all you got to do is add a cursor and move this cursor around. So the flat band gain or the passband gain here is 0 dB. So to find the 3 dB frequency, you have to go down here to find, right, C2 is negative 3.02 dB. And so this would be the 3 dB frequency or the cutoff frequency. And you can read the frequency from all the way down in the bottom of that red line. It says X1 equals 70.61 kilohertz, right? So that's how you would read the 3 dB frequency from this graph. Okay, but the key thing to get right when doing this measurement is that C1, channel 1, must be the input of the system that you're trying to characterize, and C2 must be the output. If you swap the two, then you will not get correct plots, because by default, the network analyzer uses channel 1 as the reference and channel 2 as the signal being measured. Okay. All right. So that basically is it about the network analyzer. Oh, if you wanted to actually get the data points and not just the plots, then you can go here, File, and then Export. And you can either export the image or you can export the data, and then you'll have this data for any post-processing that you might want to do. Okay, but also the image, if you want the image, then you can also export it like this instead of taking a screenshot. If you want just the plot, then you have just the plot, or if you want the entire network analyzer interface, then you'll get the scales and everything on the right also. Okay. All right, so that's how you use the network analyzer and export data from it. With that, I will end this week's lab briefing. I know it went a longer, but there was a lot of important stuff to cover this week. So if you have any questions, then do ask me or the UTAs, and we'll be happy to help. All right, good luck.